Hello everyone, thanks for joining me today. My name is Sailesh Trivedi. I am responsible for product management and cloud engineering for Oracle Database Sharding. In today's session, we will be discussing how to manage your data like YouTube, Uber, GitHub, and Dropbox at scale without having to build a lot of custom software. We'll take a look at the architecture and features built by these internet scale companies for scalability purposes. We look at the feature set which are already available in Oracle database. We'll see how we can build similar architectures with Oracle database and how we can improve such architectures with additional features available in Oracle database. YouTube uses MySQL deployment for handling all their metadata for billions of daily video views and uploads. YouTube's approach for scaling the database included adding more replicas for better read throughput and data durability. They introduced sharding to scale the write throughput and let data set grow beyond a single machine. What that means is that they took the data and they spread it across multiple shards which are running on multiple machines. They created a separate replica pool for execution of batch jobs, backups, to offload the work from the nodes which are serving the live traffic, and they cloned the whole deployment into multiple data centers worldwide for disaster recovery and lower latency. YouTube developed a middleware called Vitess, which addresses scaling challenges while hiding the associated complexity from the application layer. Vitess has been a core component of YouTube's database infrastructure and has grown to encompass tens of thousands of MySQL nodes. Vitess has a concept of key space, and we can think of that as a single logical database that maps to multiple MySQL database instances. So from an application point of view, it looks like application is connecting to a single logical database, and under the hood, the data is spread across many MySQL instances. There is a concept of shard, which it has a subset of key space data, and the data is typically partitioned by range. A shard contains one MySQL primary and many replicas. There is a separate topology service which stores the topology data and is basically providing administrative capability for this deployment. VT-Gate is a lightweight proxy component that routes the traffic to the right shard. And it also has ability to do cross-shard joins, and they are done by splitting the query. So in case you need to run a join across data which is stored in different shards, which are different MySQL physical instances, then that is done by splitting the query and then aggregating the results. There is a notion of reference table. So these are unsharded tables, but they are needed for reference purposes across all shards, and they tend to have identical data. And this helps when we have to run a query across sharded table and the reference table. Additionally, it has capabilities around replication that supports resharding, which means being able to add more nodes and redistribute the data. It has functionality around materialized views, data migration capability, as well as change notification, which means if you repartition the data and data set moved from one node to another, the application is notified about the new data placement. Uber built Schemaless, which is again a middleware component, and was used to store the core trip data. And since then, it has evolved to be used for many other use cases at Uber. The goals for Schemaless were to be able to linearly scale and add capacity by adding more servers, which means have horizontal scalability. They needed to make sure that the right availability, which is data durability, was there, and cachings don't help with the data durability, in the sense that if there is an outage, the node outage, then the data could potentially be lost. So they wanted to make sure that the data durability is guaranteed, and they also needed the ability to notify downstream components, so that they can do additional processing, and it could be decoupled from the primary trip data. They needed secondary indices, and additionally, they wanted to have operational trust in the system. That means they should be able to deploy and manage this store at Uber scale. So for those reasons, Uber built a key value store using MySQL as a backend to store JSON documents, and that allow to store the data without strict schema validation, which means there was no schema on write in a schemaless fashion, and that's why they gave it the name. So on the right side, what we are seeing is a logical representation of data stored in schemaless on the top table, and what it's showing is that there is a trip data, which is Uber trip UID, and then it has a bunch of column names, and each column can have one or more JSON document. So that way, you can store different documents, different JSON document for each trip in different columns. In the second picture below the table is showing the actual schema definition in MySQL table definition, where each of the row, which is the row key, which is a trip ID, is stored as a UID. The column names are the different columns in the top table, which could be like base, status, notes, and the ref key is actually representing the JSON document within that column. So a column could have more than one JSON document for that matter. Now, Schemaless is built on top of MySQL, and data is stored and sharded across MySQL instances. Data is sharded based on the row key, which basically represents a trip ID in the previous example, and each node has one primary and two replicas, and they use MySQL asynchronous replication. Writes always go to primary, so that they can guarantee the order of writes and not run into conflict and conflict resolution. The worker nodes, there are worker nodes which basically accept the REST call, and they route the request to the right shard. They also, the worker nodes also support capabilities like failover. In case the master is no longer available, then failover to the replica automatically when it gets promoted to be new master. Aggregation of data across multiple nodes, routing read request to replica versus write always to master. So these are the capabilities which are there in the worker node. Additionally, they do something, they call it as buffered write, to minimize the chance of losing of data. So effectively what they do is they write the same data into multiple cluster. One is the master owner of the data, and another is another cluster, just in case if the master owner data could not be replicated to the replica, then the data, because the master say went down before the replication could happen, in which case the data is persisted elsewhere. So they have done an interesting implementation around this to make sure they are protected from an outage of that. Over the time, Uber realized that they just don't want a NoSQL system, but they wanted best of the both worlds, which means schema flexibility of the document models and schema enforcement seen in the traditional relational databases. So they evolved schemaless into something called Docstore. Now, Docstore, as they define, is a general purpose multi-model database. It provides strong consistency, it provides horizontal scalability, it provides capabilities like transactions, materialized views, association, change data capture, etc. So the architecture of Docstore has a concept of table, and table looks like a relational table, and it's structured with rows and column, and it also has a schema definition, and that schema can be enforced upon write, which means at the time of insert into the table. Now these tables are sharded and distributed across multiple shards, and each shard represents a set of rows from the table. So the data in a table is partitioned across multiple shards, and partition can have one or more shard. And the storage engine MySQL is organized as a set of partition, and the data is distributed across these partitions. So basically, the data is partitioned across multiple partitions. Each partition has MySQL instances, one master, and many replicas. Tables can also have materialized views. Docstore provides strict serializability consistency model by ensuring that the writes go to the master. And there is a separate stateless query layer which is responsible for routing the request to the right storage layer. So the routing to the right shard is automatically managed by this query layer. Dropbox built a component called Edgestore. And Dropbox uses MySQL to store metadata like users, folders, shards, shared folders, emails, campaigns, security artifacts, etc. So they had challenges in terms of as the Dropbox as a company grew, their database footprint also grew, and they have lots of MySQL instances. So that was becoming an operational burden. They were resharding the data as the data was growing, and they were adding nodes, so that was becoming cumbersome. There were lack of isolation, which means an issue or a bug can not only impact one node but all the nodes, and their workloads need strong consistency, cross data region routing and replication, as well as multi-tenancy, because this infrastructure was a shared infrastructure across many products and services across Dropbox. So they built the Edgestore, which provides strong consistency. It's read optimized, it's horizontally scalable and geo distributed. Edgestore is abstraction over thousands of MySQL databases, which are basically shards. With the An Edgestore cluster serves a subset of shards, and is comprised of a primary host and a number of secondary replica hosts. So a shard, the data is partitioned across many shards, and each shard has a primary and several replica. Stores abstract the details of physical sharding from the application. So it does things like routing, object relation mapping, and ensuring that the queries go to the right shard, or even handling queries for data across multiple shards. Additionally, they had a notion of colos, and what that allows developers to declaratively say that an element of data uh, needs to be collocated, so that they can help with queries and joins. So on the right side in the bottom picture, they're showing that there are two shards, shard A and shard B, and there is a colo X and a colo Y, and the data around user and file is declaratively set to be collocated. That means when you want to see all the files for a given user, that query will get satisfied on shard A itself. Subsequently, they realized that they need cross-shard transaction as well. So, for example, if a user shared a file with another user and the data for another user is stored on a different shard, then it becomes a two-phase commit across two shards. So they implemented that capability as well. They implemented functionality around cross data center routing and replication and multi-tenancy, because it is being used by many other Dropbox services and workloads. GitHub also uses MySQL, and that houses the large portion of their data for the core GitHub features like users, profiles, repository, issues, pull requests. And they struggle to keep their system adequately sized by moving to newer and bigger machine, which is trying to scale up, and trying to do fault containment of issues. And then they decided to basically re-architect their application and define certain disciplines and approaches so that they can partition the data across multiple nodes, across multiple shards, and continue to scale. So they introduced a few concepts, and these are not they did not actually build a separate tier as such, a separate middleware component, but these are all disciplines in application development, and they change their application so that the application can benefit from horizontal partitioning and scaling of data. So they introduced the construct like a virtual partition, which basically is a grouping of database table that belong together. And they group this database table into something called schema domain. So on the right side, we are seeing three different schema domain, gist, repository, and user. The tables in this schema domains are typically or frequently used together in queries when you are doing joins or subqueries, as well as transactions. So gist on the right hand side has three tables. Gist schema domain has three tables like gist comment, gist, and start gist, and so does repository and users schema domain. The data within a given schema domain, which is set of related table, was further split across database tables by using sharding. So the given schema domain was sharded across multiple nodes. Then they implemented, they call something as SQL linters, which basically are static code analyzer, which identify any violation where the queries or transactions, if they span across multiple schema domain, then they are flagged as violations there. And query linters verify the tables, ensuring that the queries are doing joins operations in the same database queries in the same schema domain. Transaction linters verify that all tables which are used together in a given transaction belong to the same schema domain. And for mitigating any violations, they chose the approach to actually make the changes to the application code. Like, for example, rather than doing a cross schema domain join, they broke that query into two separate queries, and the join was subsequently done within the application. Or approaches like copying data from a different schema domain into a schema domain so that the joins across schema domain or transactions across schema domains can be obviated. So the set of features, if you go through and see what these different companies ended up building, includes something like a schemaless, which means the desire there is to be able to store relational, JSON, and multi-model database. There is a notion of sharding, which basically helps with partitioning the data horizontally across multiple nodes. A request router, where the application is abstracted from the fact that the data is spread across multiple nodes and the requests seamlessly get routed to the right node, or if it's a multi-shard query, the requests get routed to the more than one shard. A topology server, which is basically the metadata store for a sharded infrastructure. Multi-shard queries, cross-shard queries, where data is needed from more than one shard, and in case of updates, being able to do with two-phase commit. Key space, a concept of key space, which is a logical sharded database. Colos, which declaratively allow data to be placed of the related table on the same shard. Schema domains, which is basically grouping of tightly coupled tables, which can be used together in joins or transactions. Virtual partitions, which are distributed data partition for schemas, and then things like materialized views, triggers, data caches, replication, and REST endpoints. Oracle database has all these features which were custom built by these different companies inside natively available inside the database. What that means is we can leverage these features without having to build additional middleware. So schemaless can be leveraged or can be mapped to Oracle databases Converged database capability, where you can store JSON, text, spatial, graph, and relational different data types in the same Converged database. Oracle database has had native sharding in database starting database version 12.2. Request router request routing can be handled by shard director as well as connection pools. There is a concept of shard catalog, which serves as the topology server, which is the metadata store for the entire sharded database. Cross-shard queries are handled again by shard catalog, which can act as a multi-shard query coordinator. Key space maps to Oracle databases, sharded database construct, and then a sharded database can have sharded tables. Colos can be implemented using table families and chunks. Schema domains map to a table family. Virtual partitions map to something we call as multi-tenant or pluggable database. Materialized views are mapped to duplicate table and materialized views and things like triggers. Oracle database have concept of triggers. For data cache, we can use in-memory, timestamp. For replication, data migration, we have capabilities like data guard, golden gate, data palm, and for REST endpoints, we have something called Oracle REST Data Services, also called as ODS. So Oracle Database is the best converged database engine. We can store different types of data, whether it's relational, JSON, text, graph, special, all in the same database. We can use the same database for any type of workloads, whether it's online transaction processing or analytics, reporting, batch execution, parallel query execution, etc. And more likely than not, most of your developers and DBAs are already well versed in the skill set of coding against an Oracle database or operating an Oracle database. Here is an example of JSON store inside an Oracle database and how we can query that. So what on the left side, what we're showing is that we can create a table. In the same table, you can have rows, different columns, and one of the columns could be of type JSON. And you can insert values into the table, and then in the JSON field, we can insert an entire JSON document, and not just one document, but an array of JSON document. Subsequently, we can query the data by treating these JSON attributes as if they were normal columns, which is what the query on the right hand side is showing, where we can query the JSON attributes as if they are a column in the table. Additionally, we can mix and match in the sense we can have JSON attributes and relational column in the same query. Oracle Sharding provides horizontal partitioning of data across independent databases, uh, which means each shard holds a subset of data and there is no single point of failure. The shards are replicated for availability. We can have one or more replica per shard. It uses shared nothing architecture. That means we do not require any specialized hardware or software, and it supports massive parallel processing capabilities as well. Applications get connected seamlessly to the shard where the data resides. So from an application point of view and operation point of view, it feels and looks like a single database. For queries which need data from multiple shards, we have a component called query coordinator, which pushes the query in parallel to multiple shards. The data from the shards goes back to coordinator, which takes another pass at the data if we need to do any aggregation, group by, or joins across data coming from multiple shards, or filter. The coordinator does that, and the results are handed back to the application. The data is stored in a shard uh, by grouping them together as a table family. A table family can have one or more or many tables, as many tables as needed, and the data for the data across multiple table families is co-located on a given shard. So in this example, let's assume we have a table family which has three tables: customer, order, and line item. And let's assume we have three shards: shard 1, 2, and 3. So data for customer ID 1, 2, 3, which is Mary's data, which means her customer information, her order information, and line item information, which is all shown in red, is co-located and placed on shard number 2. John's data is co-located on shard number 3, and Peter's data is stored on shard number 1. Now, with this, when we run a query or a join, that gets satisfied locally on a given shard. Additionally, as I mentioned before, we have a component called multi-shard query coordinator, where if we need data from more than one shard and need to do additional filtering or join or aggregation, that query coordinator can do that and return the data back to the client. Additionally, we have a notion of duplicate table, which we can think of as a reference table data. So this data is not sharded data, but a copy of this data is made available on all shard. It is duplicated, is replicated to all shards. So that way we can run a query against the sharded table and the duplicate table. In this case, as a good example would be a product catalog, which is not specific to any customer. So we are not sharding the product catalog data, but we want to run a query that show me all orders or all the products which Mary bought. That query can be satisfied in shard number 2, where we can do a join between the sharded table data for Mary and the duplicate table. Under the hood, the a shard has something we call as chunks. So it has bunch of chunks and the data for the duplicate table. So chunk number 1 say has customer 1 to 1 million, their order in line item. Chunk number 120 has customer 5 million to 6 million, their order in line item. Chunk is the unit of resharding. So we support resharding, which means you can add additional node at a later point and rebalance your data across all the shards. And to do that, the data is moved in the units of chunks to the newly added shard. Or corollary, we can remove a shard and rebalance the data on the rest of the remaining shard. All of this is completely an online operation and does not require any downtime. Oracle database sharding also has components like shard director, which can be thought of as the request routing component. So it seamlessly connects application to the right shard where the data is residing, or gets the data through catalog for data if the data is for a query is spread across multiple shards. Clients get routed automatically to the right shard or to the multi-shard query coordinator for multi-shard queries. And there is a component called shard catalog that stores the shard metadata like a topology information. It acts as a coordinator for multi-shard queries, as well as contains the gold image for the duplicate table and the schema definition. Shards can be protected by replicating the data. So we can use things like Oracle Data Guard or Golden Gate for replicating the data from a shard into one or more replicas. Additionally, we can use Oracle RAC technology, which provides active multi-node database deployment to protect from an instant protection from a node failure, as well as scale out. So each shard could be, say, a 2-node rack cluster. So that way we can have many shards where each shard is protected using a rack database. Sharding also provides for centralized backup and recovery. So by executing a single command, we can take a backup of all shards, and subsequently we can restore all shards, or we can restore just one of the shards if there was an outage for just one shard. So let's see how we can improve such architectures. Now, Oracle Database has many security features, things like database firewall for deep monitoring of database messages, data redaction, database vault where it prevents admins and DBAs from accessing application data, transparent data encryption, which provides for at-rest data encryption, label security, and virtual private databases, which not only control who can connect to a database, but also enable row level security where only a certain rows are allowed to be seen by a certain user. Data safe, which does a security assessment and monitoring, and key vault to store different encryption key. Oracle Exadata is engineered to be the best platform for running Oracle database. It has its database optimized hardware. It has scale out compute, network, and storage. It delivers the fastest performance at the lowest cost. It has a smart system software where we push a lot of things like filtering of a query into the storage cells themselves, and it has several features around manageability. Oracle database is available on premises or in cloud, whether it's public cloud, including Oracle and other cloud providers, as well as cloud at customer, dedicated region, and we can have a sharded database where shards can be deployed in any of these options. where you can think of having a single sharded database where some shards are in Oracle Cloud, some are in third-party cloud, some shards are on premises in your data centers, or some are in dedicated region. So how to improve such architectures further? There is no need for you to reinvent the wheel. You can focus your developers on adding value um, in the areas of application which help with the domain and the functionality uh, for which you are competing. This allows you to free up your engineers to work on the key capabilities of your product, and you can use Oracle support, so you don't have to build your own engineering team to just maintain your database. You can use cloud to improve things like elasticity, security, availability, manageability. These are all the features which are available in Oracle database, and these are the same reasons why you don't write your own operating system. So to summarize, all custom built features which we saw in different case studies are available natively out of the box in Oracle database. Additionally, Oracle database has many features which we looked at, like Exadata, real application cluster, security, manageability, backup recovery, active data guard for offloading your read traffic, reporting, creating your reader farms, parallel query, because if you have a lot of data which is spread across many nodes, for analytic purposes, reporting purposes, you need to be able to do scatter gather, and that's what parallel query in sharding allows us for. Things like online indexing, online table redefinition, which means you can change the schema definition of your tables without incurring any downtime. Hybrid columnar compression, which allows the data to be accessed in a columnar format instead of row. Additionally, it gives you an order of magnitude of compression so that you can conserve your storage usage for large data set. It has capabilities like secondary indices, sub-partitioning, and sub-partitioning helps with ensuring that your query performance stays constant, highly performant, irrespective of the volume of data you have. Database has machine learning, blockchain table, JavaScript execution inside database, queuing and event streaming, in memory, persistent memory, to name a few which can help us with such architectures. So in summary, Oracle Database Sharding enables internet scale application. It can be used for both structured data and unstructured data. It can be used for both online transaction processing applications as well as analytic workloads. It can be deployed on premises or in cloud or in hybrid models. Oracle Database has additional features which can help improve such architectures. Oracle Exadata is the best platform for running Oracle sharding. All these internet companies hand built their own sharding solution because they did not have good alternate at that time. Now you can get the world's best sharding along with the mission critical, highly available, scalable, parallel, secure database capabilities that Oracle is known for. Here are some additional resources, and feel free to reach out to me if you have any further questions. Thank you so much for your time, and have a great day.